begin. Hello and welcome to another Bitwise homework day. Today we're going to be looking through these papers that pair linked. I don't remember what, guess I don't have Yeah, okay, so let's see here. I don't remember which days they were, but yeah, day 9, he linked a paper for us to read. He didn't explicitly say it's homework, he said it's fun. But of course we're going to be doing all those too, so I'm going to read through the papers he's linked. And then the other one was this one right here. So I'm going to start on the day 9 one, which is compiler construction, the art of Nicholas Worth. And again, I know I'm butchering his name, but that's okay. Apologies to the man. So, the abstract here, Nicholas Worth is not only a master of language design, but also a pioneer of compiler construction. For 4 decades, he has refined his techniques for building simple, efficient, and reliable compilers. I mean, that kind of follows from being a master of language design, in my opinion. If you're designing languages, you kind of need to be, you know, good with compiler construction too. So I think it kind of follows from him being a master of language design that he's also a pioneer of compiler construction. Just my little opinion there. But this paper tries to collect some general principles behind his work. It is not a paper about new compilation techniques, but a reflection about Worth's way to write compilers. Yeah, I mean, I guess that's true, risc-v. If you're an armchair language designer, you might not be versed in compiler construction. So, introduction. Among the numerous research topics that Nicholas Worth, they're going to be saying his name so many times in this paper, aren't they? And I know I'm pronouncing it wrong because it's like the Worth is pronounced with like a V or something, because it's you know, some European name. But you're just gonna have to bear with my pronunciation here, my American pronunciation. It says, among the numerous research topics that he approached during his professional career, programming languages and their compilers clearly was the dominating theme. There is hardly anybody in computer science who has such a deep insight into language design as Nicholas Worth. Since the early 60s, he has been active in this field and has contributed such seminal languages as Algol W, Pascal, Modula 2, and Oberon. And being an engineer, he was always as much concerned about the simplicity and efficiency of his compilers as about the elegance of his languages. In this paper, I will try, who's the author? Hans-Peter Mosenbach. I'm positive that is a butchering of his pronunciation too, but yeah, that sounds right. Veer, something like that. I'm just gonna continue to call him Worth. So in this paper, the author will try to summarize some principles of Wirth's art of compiler construction. Although I have no personal recollections from Wirth's early projects, I have studied his compilers from the early 80s on and was lucky to have the chance to work with him for several years during the Oberon project. Okay, so this is someone who helped out with the Oberon stuff, apparently. So this paper is more about what I learned from him and what I appreciate about his work. Wirth himself gave a much more thorough description of his compiler technology in his recent compiler book, in his Turing Award lecture, and in his recollections at the second conference on the history of programming languages. And I think the compiler book they're referencing here is the one that Per referenced early on as well. When I write about Wirth's art of compiler construction, I also want to honor the work of his colleagues and assistants, of which there are apparently numerous. However, although many of the well-known compilers from ETH Zurich were implemented by his bright PhD students, it was always Wirth who set the direction and determined the style of ETH compilers. I will start this paper with some general principles that I learned from Wirth, and then look at more detailed guidelines and techniques for the individual compilation phases. Okay, so that's chapter 1 here. Let's go on to 2, guiding principles. Besides using specific techniques, data structures, and algorithms, it is also important that a compiler designer follows some general guidelines which set the framework for the whole development. Here are a few principles which I believe to be central in Wirth's compilers. The list is perhaps incomplete and somewhat arbitrary, but hopefully still some food for thought. Use straightforward techniques. I mean, I think that one applies pretty broadly to any software, right? Most of the time, like, a good rule of thumb is you wanna use straightforward techniques, I think. I feel like that's much broader than just compilers specifically. Yeah, it definitely is easy to forget that principle, that's true. Compiler technology is one of the most intensively researched fields in computer science. Oh, and you know, that reminds me, just as an aside here, unrelated to this, but when it comes to, you know, general rules of thumb that you probably want to follow, my eye's wandering a little bit, but when it comes to rules of thumb that you might want to follow, there was a good tweet I saw recently by Mike Acton. Yeah, and this one too by Fabian. These both were pretty good. Where's the one? Here it is. Mike Acton approximator. So the tweet this originated from was what 5 words best describe programming? And Philip Bach, again, I don't know if I'm pronouncing his name correctly, he said, what would Mike Acton do? Which I definitely agree with. I think that's a very good way to think about programming. Okay, so risc-v says, that's actually one thing I'll try to stress in my DeCon presentation when talking about how I went about to design symbol. I just started from easy cases and generalized progressively instead of top-down, object-oriented UML diagram madness. I'm really looking forward to that talk. When is DConf? dconf.org. I know it's coming up soon, right? May 2nd to 5th, I guess. So yeah, that's pretty soon. Awesome. Which day are you talking? I haven't looked to see the speaker list or anything. Schedule. I know we're going way off topic here, but I am very curious about the DeCon schedule, so bear with me here. uh, let's just look over the schedule here. Day 1, taking advantage of D within existing C code bases. That's definitely going to be a good one from Walter. A decade of D. I'm not familiar with these people, I don't think. So I don't know how good that one will be. We'll see. Exploring D via benchmarking. Oh yeah, so the eBay has done some D stuff. That's going to be an interesting one. Building a scalable web app with Angular and D. That one doesn't sound super interesting to me, but it's by Extra Worst, so I'll definitely tune into that. He's one of the people that I did actually talk to at DConf 2016 because I sat at, you know how they had the tables outside of the conference area in the Berlin venue for lunch. So I sat at one of those tables one time for lunch, and I'm pretty introverted, so I'm not the kind of person who goes up to anyone to talk to them. But a bunch of people ended up sitting at that table, and Extra Worst was one of them. So he ended up talking to me some. So that was interesting, getting to meet him and talk to him. How to convert your rusty old lamp into a shiny new Vibe app. That'll probably be a funny talk. We'll see how that one goes. D for the blockchain. Okay, that one might be interesting. Ask us anything, that'll be good. Systematic introspection into the D language, that's going to be a good one. Unified concurrent runtime for D, that sounds interesting. Porting D to a non-Windows, non-POSIX platform, that sounds interesting too. Yeah, it's too bad that we missed each other. It would have been really fun to talk to you. Okay, so here's your talk, Beyond Object-Oriented Programming, a case study. So that's day 2. Awesome. I'm definitely going to be watching it. Tuned in live, of course, through the live stream. Open methods for D. The expression problem solved. That sounds like it might be interesting. That sounds kind of similar to in the same vein as yours of taking stuff from what I would consider the object-oriented programming world and, you know, looking at classic problems and seeing how they apply to D. That just from the name of this talk, that sounds like what this person is going to be doing as well. Yeah, that's what I thought. It sounds related. Expose D, the war stories of an inspiring D compiler developer. That sounds good. Showcasing collections. That sounds like it might be good. Lightning talks. I always enjoy the lightning talks. Day 3. Oh, cool. That's really awesome that you were able to coordinate those talks. That'll be really good then. I'm looking forward to seeing those two and seeing how they relate to each other and how they're coordinated. How to abstract over context. That sounds pretty pretty general. I wonder what that'll actually be about. Although VM backed goodies in LDC, that's going to be a good one. Overview of DXML and lessons learned. I recognize the name Jonathan M. Davis. I didn't talk to him, but I know he's prolific in the D community. But if DXML is an XML implementation, that doesn't sound super interesting to me personally. But I'm going to watch all the talks probably. Binderoo, wait, what do you mean you quit your job? That sounds like it'll be a fun one. Adoption of D for genomic bioinformatics. That sounds interesting. Project Blizzard, safe memory allocation and deallocation. Oh, I've got an alarm going off. Sorry about that. Oh, really? Martin's the Scala creator? I did not know that. That is really interesting. Using D as the programming language of choice for large-scale primary storage system. What's that company that this guy's from? Weka.io or something like that? I know that he's given talks in the past of their use of D. Announcing Mecha. I don't know what that's going to be. Oh, and then just hackathons. So I assume the hackathons aren't going to be live streamed. I wonder if this is going to be live streams. Yeah, Weka. I guess they're releasing some of their code or something. That's interesting. So yeah, I'm very excited as always to see the DConf talks. But getting back to what we were looking at, that was kind of a sidetrack upon a sidetrack, but your alarm is a small guy inside a little box like in Discworld. I don't get the reference. I have not read Discworld. But Mike Acton said this is how you would approximate his thought process, basically. The first step is asking, can we not do this at all? Then, can we do this only once? Can we do this fewer times? Can we approximate the results so no one notices? Can we use a small lookup table? Can we use a small FIFO? Can we constrain the problem further? And then recurse. And he also says, this is assuming you ask what's the most common case as well, and what problem are we actually trying to solve. So I think all of those are some really good, a really good look at how you should think about problems in programming. It's, those are a lot of really good questions to ask yourself. And he's even given you the ordering to do it in. But yeah, I kind of want to like write this down somewhere, have it like on a sticky note so I can always look at it and be reminded to ask myself these things. I think this is definitely a good idea to kind of follow this thought process. And then Fabian had some top 3 benchmarking mistakes. Are you using a relevant test set? Are you even testing the right thing? Does your test give consistent results if run repeatedly? Have you verified that you're measuring what you think you're measuring? So yeah, all of those all sound like some good things if you want some good rules of thumb for programming. There you go. But getting back to what we were actually reading. So that all started because of this rule of thumb right here. But compiler technology is one of the most intensively researched fields in computer science. There are highly sophisticated algorithms for syntax analysis, semantic analysis, optimization, and code generation. However, more sophisticated techniques do not necessarily lead to better compilers. Worst compilers use only the simplest techniques such as recursive descent parsing, context-free semantic analysis, and single-pass code generation with only a few optimizations. Nevertheless, these compilers generate sufficiently fast code and run much faster than most commercial compilers. A compiler writer should have the heart to refrain from using highly sophisticated algorithms if he can see the more straightforward techniques are perfectly sufficient. In his Turing Award lecture, Wirth wrote, within the Euler, AlgolW, and PL360 projects, much consideration was given to the development of table-driven, bottom-up syntax analysis techniques. Later, I switched back to the simple recursive descent top-down method, which is easily comprehensible and unquestionably sufficiently powerful if the syntax of the language is wisely chosen. Then we have simple compilers are more reliable compilers. As in any software project, it is essential, and again, as an aside here, I should say this is kind of true of any software. The simpler your software is, and the smaller footprint that your software has, the smaller surface area that it has, it's going to be more reliable, it's going to be easier to understand, it's going to be hopefully less buggy. It's going to be if it's a smaller surface area, you're constraining the problem in terms of like security issues. The smaller the better in that regard. So I think keeping things simple in general, again, kind of it's a good principle just in general, not specifically for compilers, in my opinion. As in any software project, it is essential that a single person can grasp the whole design of a compiler. This is what Brooks calls the conceptual integrity of a software system. It can only be achieved if the compiler is simple enough. And again, I think all of this applies to any software. And you can argue today that really, there's really big software out there. And it's like, can any single person grasp the whole design of the Linux kernel, for example? But I think, if a piece of software is designed well, even if it's huge, I think the answer is yes, or at least yes to a subset where you can jump into the code base and do useful work in it, and you can pick up as you go everything you need to understand about the bit you're interested in. If things are designed well, you can easily read the code and understand everything, or everything you need to understand to be productive within the code base. For example, I ported Milton to Linux for my series, and I didn't need to read the entire program and understand every little bit of it, but I was able to jump into that code base because it's really well structured and well written, because Serge is an amazing programmer. I was able to go through the Milton source and very easily add the support for what I needed to run it on Linux. And then I was even able to go through the bits about the graphics pipeline and learn what I needed to learn about OpenGL and his code to implement features that I wanted in my fork of Milton. And that's the kind of thing that I think follows from just structuring your code well and being an experienced programmer. Knowing how to write a good code base leads to that kind of thing where someone can jump into the code base and understand what's going on and be productive in it. He says, a compiler that cannot be understood as a whole by a single software engineer cannot be guaranteed to be correct and cannot be maintained without introducing new errors. In his Turing Award lecture, Wirth confessed that this modular compiler is already at the limits of comprehensible complexity, and I would feel utterly incapable of constructing a good compiler for Ada. Generate good code for the frequent case. Don't optimize for the exceptional case. And again, this is really good advice regardless of compilers. I think this paper is just going to be good advice for programming in general, not specific to compilers at all, because so far everything has been good advice for just programming in general. This is a great rule of thumb for optimization. You don't optimize the exceptional case. You want to optimize the most common code path that's going to be the hottest, that's going to be, taking up the most time in your software. If you're trying to optimize for the cases that aren't common, then you're kind of shooting yourself in the foot, because most of the time that optimization isn't going to matter, but it's adding complexity to your program, and it's not a good trade-off. And it can also be detrimental if it hampers the common case, right? Like if you have a ton of code to handle something that rarely happens in your software, but it's really, it's a really beefy amount of code because it's highly optimized, like you've unrolled a bunch of loops and stuff like that. Now, the problem with that is that your common case, if it's buried under all that code for the exceptional case, now you're going to be, really hurting performance because of, like the iCache, the instruction cache is going to get filled up with all that code for the exceptional case that's not going to get run most of the time, and then you need to go fetch the code for what you actually need to do most of the time, and you end up hurting your performance rather than helping it. So, this is just a good rule of thumb in general. It is much more important that frequent language constructs such as procedure calls, array accesses, or general construct structures are compiled efficiently than to put too much effort into optimizations such as loop unrolling or induction variable analysis that can only be exploited in rare cases. So they're talking about actually in the efficient, like how good the code generation is for the compiler. They're not talking about optimizing the compiler itself, but in the code generation that it spits out. But the same principle applies. Too much effort into those optimizations that can only be exploited in rare cases. Worse compilers don't use any of the more advanced optimization techniques. Instead, they generate good code for ordinary programs by fully exploiting the machine architecture and its addressing modes. Next up is generate good code from the beginning, don't generate bad code and optimize later. And that, I think, goes to with the way I'm designing Hula, which if you follow the Bitwise homework series I talked about on the first episode, the idea there is to not optimize pretty much at all, except for a few cases where it makes sense to do so. But the idea isn't to generate bad code that you have to optimize outside of the compiler. The idea is to generate good code from the beginning, where good code isn't optimal code, but it's like what you would write naively by hand in assembly, right? You want to generate something that's reasonable. And you want, the best way to go about that, in my opinion, is for the language, the constructs in the language to be structured in such a way that they naturally translate down to something very similar in assembly. So you naturally write something that's somewhat good, somewhat optimal by hand, and it just naturally ends up generating good code as a side effect of that. Some compilers first generate poor intermediate code because it is optimized later anyway. For such compilers, it is often reported that optimizations achieve substantial speedups. However, this is not surprising since the unoptimized code was rather inefficient. If a compiler generates good code from the beginning, there is much less room for speedups. Brandis and others report that non-optimizing Operon compilers for the Motorola 68020 or the Sun Spark and for the DEC MIPS architectures generated good code that was as efficient as the code generated by the standard C compiler with the optimization option switched on. Only for the IBM RS6000, the optimizing C compiler was able to generate more efficient code than the Operon compiler. Next up is don't let the compiler repair poor programming style. And again, that's what I was kind of saying with the one before it too, with this one here. That's kind of the idea there, right? Like the language should help you program in a good style that's going to generate good code. But it's also not the compiler's job if you write really bad code to turn it into something good. It makes more sense for it to be a very simple transformation of, you know, you can easily reason about, here's my code, here's what it's going to generate in assembly. So you can still think kind of on the level of assembly when you're writing your higher level code, and you'll very easily understand what the compiler is going to be doing. You don't want the compiler to be overly complex and take something that's written absolutely horribly and transform it into something completely different that ends up being more efficient. I think that's, again, it's not the right trade-off for complexity in the compiler. Some people expect a compiler to smoothen inefficiencies caused by poor programming style. This includes some cases of common subexpression elimination, loop invariant code motion, and copy propagation. It is, however, simpler and often also clearer if the program does these transformations in the source code instead of relying on the compiler to do them behind the scenes. And again, that's exactly what I'm saying. Like, common subexpression elimination is a great example where what common subexpression elimination is if you have a block of code and you refer to a subexpression multiple times within it. For example, if you have a block of code where you have a lot of cases, let me just I wonder if I can give you an example here or something. I don't know if I have a good example, but if you have a block of code where you're doing array accesses, you're accessing a variable in an array, and you type that array access multiple times. Like, say you have a block, and you're typing along and you're saying like if so you have some array and you say like A0 equals 42, then you say like A0 equals 0, else A0 equals 1,000, A0 times equals A0. risc-v says, I'm not sure I agree. If this code is not performance sensitive, I just go for the most clarity. If that's with redundant subexpressions, so be it. I think that's fine if I feel like that's fine, but you shouldn't expect the compiler. I mean, if you're programming in C or you're programming in D or something, then you certainly can expect the compiler to do that because that's what those compilers do. But I think for designing a thing from a language design perspective, I think a compiler shouldn't be expected to do that common sub-expression elimination for you. If you don't care about the performance and you prefer the clarity, then you should also understand that you're going to be taking the performance hit because it's not going to do the common sub-expression elimination. So what common sub-expression elimination is you can say like, you know, int v equals a 0 Oh, does it not like the brackets? Well, let's just do it by hand. And this isn't actually correct. You'd want it to be something more like this, I guess, because we were writing into the array. So it's not a good example, but you get the idea, right? That's kind of what common sub-expression does. risc-v has a better example of common sub-expression eliminations where you have this b times c and then b times c is computed again right here. The b times c can be factored out. That only needs to be computed once because it's going to be the same both times, right? And again, I agree with you, risc-v, that I think it can be clearer in some cases to not do the common sub-expression elimination by hand. But again, I don't know if you're preferring to not do it, I don't know if you necessarily want the compiler to do it for you either. I feel like personally, and maybe this comes down to personal preference, I guess, but personally, I would rather the compiler not do the common sub-expression elimination if I write this, right? And what I would prefer is that if I wanted to eliminate that common sub-expression, then I would actually go in and optimize it by hand and factor that out. And furthermore, another thing you can do is you can have a tool that automates that process for you, that detects the common sub-expression elimination, not the compiler doing optimization, but a separate tool that analyzes your source code and detects this and is able to do a rewrite for you. And another thing is you can leave a comment saying this is the original code and then also have the optimized code like after it in the source code. And one argument there is, well, what if the comment gets out of date, which is a common problem with code comments. And another thing to that is, well, it doesn't necessarily need to be a code comment. It could be, you know, a system that does diffs, you know, that does like keeps a list of patches, like sort of like a git history. And then, you know, it automatically makes sure everything keeps in sync. Another thing you could do is have an actual language feature where you have built into the language a thing where you provide the original and its transformation. And while that might not actually be that practical, because then the question is, how does it make sure that you haven't modified it since you wrote it? So you maybe want something more like a Git kind of system to track that for you. But risc-v says, but you might not see that code. It might be the result of macro expansion, function inlining, etc. After all of that, it might have a sub-expression worth eliminating that was not present in the straightforward source code. That's true too. And I guess I don't have a good answer for that, how you would really address that. I mean, when it comes to something like function inlining, this again goes back to my preference that I don't think the compiler should be deciding the inlining for you. I think you should be in full control of inlining as the programmer. And something like macro expansion, it depends if you even have macros in your language like that. You might not even have that level of complexity. I mean, I just don't know. I don't know if that really is a situation. It kind of depends on the language design, honestly. I feel like if the language makes it easy to end up in this sort of situation, then it becomes a problem. But I don't know if you necessarily want your language to be designed in such a way that that's the kind of code you write in the first place, if that makes sense. But I might be wrong about that too. I haven't thought about that in much detail. So you make a good point that's worth thinking about, definitely. risc-v says that's orthogonal to the argument. It might be an STD algorithm that was inlined as requested by the lib author. That's true. But again, I still don't really see a concrete example where you kind of end up shooting yourself in the foot if you don't let the compiler do that for you. I still don't know if it would really be a problem in practice or not. But this apparently is what Worth prefers, of not letting the compiler do those sorts of things for you. Although not all of these transformations can be expressed in source code, most of them can, and the remaining ones usually don't cause major inefficiencies, except in some frequently executed inner loops. Alright, have a good dinner, risc-v. I'll see you later. Thank you for tuning in. Next we have generate predictable code. Optimizations often have the effect that minor changes in the source code can cause major differences in the runtime of the program, because a small change in the code may allow or disallow an optimization. Programmers feel uneasy if they cannot predict the behavior of the generated code. It impedes debugging and benchmarking. And again, this is one of the major reasons that I personally don't like the way optimizing compilers work today, and would prefer a language where the generated code is very predictable and very I like to say isomorphic, but I don't know if that's really the the proper term for it, but very maps very closely to the original source code. It's something that I prefer because it makes it much more easier for the programmer to reason about it. And I like the idea of having tooling external to the compiler that is more interactive with the programmer to do optimization. And that's something that Dono Knuth talked about as well. And I remember someone pointed out that Daniel Bernstein, I think his name is, had a similar opinion too, And I looked up the slides that they were talking about. I don't remember who mentioned that, but I looked up the slides of his talk that he gave, and he did in fact reference the exact same paper by Donald Knuth that I was talking about, that I referenced as well. So there seems to be a common school of thought here among many people. I'm not saying it's necessarily correct. risc-v might be right that a more optimizing compiler is really the better way to go. That certainly is what has prevailed today. That's what most compilers are today. So maybe that is the proper way to go. But I'm more interested in exploring the simpler approach that this sort of thing is talking about personally. And that's what Per is doing too in Bitwise in his Ion language. What is difficult to compile is usually also difficult to understand. Like a programmer, a compiler has to analyze, that is, to understand, a program before it can translate it. If a language construct is difficult to analyze for a compiler, it is often difficult to understand for a human. For example, in C, the construct x parenthesis asterisk y parenthesis and then parenthesis semicolon declares a function pointer y, whereas the syntactically similar construct x parenthesis asterisk y parenthesis semicolon denotes the call of a procedure x. Since both constructs can occur at the same place in a program, it is difficult to keep them apart syntactically, both for the compiler and for the programmer. Instead of applying more sophisticated compilation techniques, simplify the language. And I feel like a lot of these are kind of redundant or kind of repeating the same thing over and over. I feel like we're kind of beating a dead horse at this point. Of course, this advice can only be followed if the compiler writer is at the same time also the language designer, as Wirth always was for his compilers. If the implementers of C did not rely on powerful compiler construction tools such as Yak, the syntax of C would probably be simpler. Strive for short compilation times. It is that, one thing I wonder, is that true that C was designed using stuff like Yak? I didn't know that, if that was the case. That's kind of interesting, and if that's true, that does kind of bring some insight in why the C syntax is what it is. That's something that later languages have tried to fix, like D, for example, has nicer syntax in various areas because it's, D is designed in such a way that it's better for compilers, and it also ends up being a nice syntax for programmers too, in my opinion. But yeah, that does kind of make sense, that if they weren't thinking about the details of how things would be lexed and parsed and things like that, and we're letting compiler construction tools do it for them, then I can understand why they would have made some syntactic choices that are kind of hairy under the hood. If they weren't reasoning about what this was actually going to boil down to under the hood, then of course you end up making mistakes like that. And that's why that's in my opinion why you really want to be close to the metal and programming at a low level when you're writing like a high quality piece of software, and you don't want to be at some super high level of abstraction, because you really want to be thinking about what the computer is actually going to be doing. And the more you pile on top of that, the harder it is to reason about what this is actually going to boil down to. And it also tends to be the case that as you build abstractions on top of abstractions on top of abstractions, that you end up introducing lots of overhead along the way too. But I'm not saying that you don't ever want something like that, because programming at a very high level is very useful if you're doing something like scripting, where you don't necessarily care that the code it generates is as perfect as it could possibly be, and all you want to do is think at a very high level and solve your problem and not worry about those details. And it doesn't matter what it ends up doing, because it's not something like, something that you're trying to ship as a quality product. It's just some throwaway code to, figure something out or something. That's in my opinion the place for very high level of abstraction in software and things of that nature. He also says strive for short compilation times. Again, I don't know what, before I read this actual paragraph here, I don't know what their reasoning is for this, but I know Jonathan Blow's reasoning for this, which is that and also in D too, this is something they stress in D as well, that fast compile times, the better your compiler is at compiling quickly, the shorter the iteration loop is for the programmer, and that actually does make a really big difference in terms of the flow in your mind of when you're in the zone, so to speak. It helps with that, and it also helps with just saving time over a large period of time. Waiting for your compiler adds up, even if it's just a few seconds. Well, if you're compiling, tons of times every day for a year, pretty soon those seconds add up to a significant amount of time that you're just sitting around waiting for your compiler to compile your code. And that's kind of something that Jonathan Blow has stressed, I believe, if I'm remembering correctly. And that's the kind of thing that you really notice when you're used to thinking about really, small amounts of latency. Like a game developer, for example, is someone who's very tuned to this sort of thing, because they're used to, making sure their game is running at like 60 frames a second or something, and there we're talking about, frames that are like, 16 some milliseconds. And so someone who's used to that environment, very small, latencies do suddenly matter a lot to you. And if your compiler is taking, a second to compile your code, that's an eternity, especially if it could be doing it practically instantly. And I'm not saying this is just a problem to people who are game developers, for example. I think it matters for everyone, but I'm just pointing out that I think depending on what your mindset is, what you're used to, some people don't even realize it's an issue, or don't even realize it's a problem if their software, for example, is slow and has a lot of latency, because they're just, they're used to it. They don't think about those things. I think there is a lot of kind of like a psychological element to that, of the brain and how it filters information, and how it adjusts to different things. I was talking to Delix about this recently. Well, not super recently, but not terribly long ago. And I was mentioning how I remember reading about an experiment where they like had some sort of thing that you look through that flips the image upside down, right? So, you'd walk around with this thing on for a while and you're seeing everything upside down, and their brain would actually adjust to this, and you'd start seeing right side up again. But then you take the thing off and you're seeing upside down again, because your brain hasn't adjusted yet. So even though the image is coming directly to your eye, you're still seeing it, wrong because your brain is doing that kind of filtering and adjusting for things. And so it takes a while for your brain to adjust again and start seeing the right way up again. And that's another thing, like, just this is something that if you wear glasses like me, if you have really bad eyesight like I do, taking your glasses off and uh, you know looking at, like, in the morning, if I'm looking at my phone and doing stuff on my phone and I don't have my glasses on, I'm just lying in bed and I don't have my glasses on or anything, and I'm going like this for a while, and then I put it down and put my glasses on and I try to focus on anything, I can't, because my brain needs to adjust to the massive difference between my actual eyesight and what my glasses correct it to. And that's also something that happens when you get a new prescription of glasses, where you put on the new glasses and everything, you can't focus on anything at all. It's absolutely terrible because your brain hasn't adjusted to the new prescription yet, and it takes a while to adjust to that. But once your brain adjusts to it, you can focus on things just fine. You can see everything just fine. Uh, and that kind of, highlights how much the brain is actually doing compared to the senses of what the actual raw data you're getting in, and what you're experiencing. And another thing is, for example, your eyesight. Another thing about eyesight is there's actually a blind spot where the like the retina hooks up to, I don't know the details, but I'm no biologist, but where it hooks up, there's actually a blind spot there, and your eyes actually, like, your brain actually does like a linear interpretation or interpolation over that. And I think it also, because you have two eyes, it's able to figure out what's in the gaps there. But like, the actual raw input of what your eyes are getting and what you perceive is actually very different. The brain is really good about doing that kind of thing, and I think that actually really affects what you perceive in terms of something like the latency of software. Um, that's just a little personal insight on that. I think there is a lot of kind of psychological elements to that. But I also want to stress that I think, even though that's true, that the brain will adjust to things, I don't think that's an excuse for writing bad software. I think you should strive to write software that's, very snappy and immediate, and does everything very efficiently and fast and is very responsive. Just because someone's brain will adjust to it and tolerate it if it isn't, doesn't mean that you should try to get away with it, right? You should still try to write good software, regardless of what people's brains are willing to put up with. But let's actually read what this person is saying about this. It is not only important that the compiler generates efficient code, but that it also runs efficiently itself. These two goals are often in conflict, and one has to find a reasonable trade-off. Unfortunately, many commercial compilers emphasize code efficiency and accept long compilation times. However, even a compilation time of 5 to 10 seconds per module can be perceived as unduly long, especially if several modules have to be recompiled after a program modification. During software development, the productivity of programmers can be boosted significantly if their work is not disrupted by unduly long compilation pauses. So yeah, that's pretty much what we were saying about, the reasoning behind like DMD being a fast compiler and Jonathan Blow's language having a fast compiler. That's, this is talking about the same sort of reasoning. A compiler is also an educational tool. It should inhibit bad programming style. And I think I already touched on this too, that but let's read it. Clearly, a programming language can have an educational effect by providing only clean and structured language features, but a compiler can have a similar effect by introducing certain restrictions which limit the size of a module, the number of imported modules, or the number of global variables to a reasonable maximum. That's an interesting thought. It can also penalize questionable programming constructs, such as the access to non-local variables, by not optimizing such cases. Although these measures are not very popular with programmers, they can have an educational value and may prevent major style deficiencies. Such restrictions are a problem, however, when source code is generated by a tool. In that case, the length of names or the size of modules cannot be influenced by the programmer. So yeah, I don't know if I totally agree with this myself, with the idea of introducing restrictions such as limiting the size of a module, the number of imported modules, the number of global variables. I mean, in terms of implementation, I think it does make sense to potentially have a hard upper limit on those, but I don't know if you want it to be, I mean, they say a reasonable maximum, but I feel like you'd want it to be a very large maximum, that you really don't want to restrict people too much in regards to these things. But I don't know. That's not something I've ever thought about before. the limiting those sorts of things is not something I've thought about. Now, I mean, penalizing questionable programming constructs such as the access to non-local variables by not optimizing such cases. I mean, saying penalize is, in my opinion, not the right way to phrase it, because you're not going out of your way to make something that's bad style be slow. It's just that you're not doing the optimization on it. And that goes back to, all the things we were saying before about how you should generate predictable code and, have it be very straightforward what the compiler is doing. Just not doing optimizations on global variable accesses, for example, I think is perfectly reasonable to, to not go out of your way to optimize something. It's better to let the programmer, write good software to begin with than rely on the compiler as a crutch, right? A compiler should be a tool, not a crutch. I think that's the kind of the takeaway. Although these measures are not popular, yeah, we read that, didn't we? Such restrictions are a problem. Oh yeah, we read all of this. But yeah, I think when it comes to the actual programming language, providing only clean and structured language features that promote good programming style, like, well, they map nicely to good code that you want to be writing. Having your language help you write good code by just encouraging, the actual structures that the language provides mapping well to assembly, that's definitely something you want to do, I think. But when it comes to the compiler imposing, I don't think you should impose artificial limitations just to try to encourage the programmer to be creative. I think it definitely does have an educational effect. And that's something that Donald Knuth talked about too in the structured programming with GoTo paper. He talked about that as well, about how being in a very restrictive environment can really bring out the ingenuity of a person, and it can be very fruitful. And there's certainly a whole tradition of that in art as well, or like writing, like constrained writing is a perfect example of that. I think that's a well-known thing, and I can definitely relate to it personally too, in that I started with the TI 84 Plus calculator, and I started out with TI Basic, which is not close to what you can do with assembly on one of those things. I can definitely relate to the being in an environment where you're very constrained and how it can bring out a lot of creativity and ingenuity and be very educational for you. I think that's very true. But for your compiler, I don't know if you really want to impose that intentionally to try to bring that out in people. And that's something that Donald Knuth talked about too, of you don't really want to impose limitations on people just to try to get that experience out of them. And people won't like it if you do that. But I don't know how you go about it to encourage people to experience that sort of environment for themselves to get that educational experience. I don't know what the right way is to do that, but I think it's definitely not imposing artificial limitations in your compiler, for example. But I mean, something like having maximums, they can be a reasonable thing to do if you want to avoid dynamic allocation. It can make a lot of sense to have a fixed size buffer for something, or have a hard upper limit cap on something. But that's more of a technical decision that you make, and you want to make it in such a way that it's not going to restrict people too much if you need to make that kind of decision. But if you can get away with having no upper limit at all and just letting the compiler use up as much memory as it can if it needs to, can be a reasonable approach too. So, I don't know about this one, but there's nuggets of good ideas in this one, but I don't know if the whole thing as a complete package here is really what you want to do. But there's definitely good ideas in this, like don't optimize bad code. There's value in being in an environment that's constrained for, educational purposes. You might need some maximums for technical reasons. But yeah, I think this one, I guess what I'm trying to say is this one has good information in it. It has good ideas in it, but you need to be careful not to take this to mean impose artificial limitations, because I think that is not a good idea. I think that's the wrong approach. That's what I would say about this one. Write the compiler in its own language. That's something that we're going to be doing too. I think that's a great idea. It's acts as its own test suite, so to speak, and it's a great test of the language, of the features of the language. It makes sure it gives you your compiler a reasonable sized project to work with, so that can be useful for testing performance. It's useful for a whole number of reasons to write the compiler in its own language, and most languages do this. It's kind of a tradition among programming languages to be self-hosting, and that's something that I plan to do with the Hula language as well, to have it be self-hosting. And of course, well, actually, I don't know if Pear is ever going to have Ion be completely self-hosting. I'd be kind of surprised if he doesn't do that at some point, but I believe he said it's not a big priority either. So that might not happen for some time, or maybe not at all. I guess only time will tell what Pear decides to do. But let's see what this guy has to say about this stuff. For Worth, language design and compiler construction always went hand in hand. He writes, I never could separate the design of a language from its implementation. For a rigid definition without the feedback from the construction of its compiler would seem to me presumptuous and unprofessional. Writing a compiler in its own language not only proves that the language is powerful enough, but it has also the advantage that any improvement of the generated code will make the compiler faster too. Yeah, I just think there's a lot of good reasons to do that. I think that's a good way to go. Other people will probably find even more principles. Wirth himself published some general compiler guidelines in an early paper, but I wish he would do it again today in the light of the Modula and Oberon projects. In the remaining sections, I will look at the individual compilation phases and try to extract some general principles from them. Chapter 3, Scanning. There is not much to say about scanning. Wirth scanners are handcrafted and optimized since the scanner is one of the most time-consuming parts of the compiler. Token positions for error messages are recorded as character positions and not as line column pairs, which simplifies bookkeeping. That's interesting. I think pair does do line column pairs. I'd have to double check the code. Maybe he does just do character position. I don't know. But that's an interesting idea. Attributes and token positions are returned in global variables to avoid parameter overhead for information that is not needed with every token. The length of names is restricted to a reasonable amount, 24 or 32 characters. This can be seen as an educational means since unduly long names can inhibit the readability of programs as much as cryptically short names do. And again, this kind of gets into the same thing of, I don't know if you want to impose artificial limits on the programmer. 24 or 32 characters though, I mean, that is pretty reasonable. You do want, I think, a hard upper limit on that, on the length of a name. But, you know, I think something like 24 or 32 characters is maybe pretty reasonable. But, you know, I don't think it would be too terrible if you went with like 64 characters or something. 24 might be a little bit on the low end, I think. But, you know, you want something where nobody in their right mind is going to write, you know, a name that's ridiculously long. So there's no good technical reason for you to support arbitrarily long names, and there are good technical reasons to have it be fixed size, right? So that's a case where it does make sense to have a hard upper bound, and I think they're right that you should restrict it to a reasonable amount. But I don't know if 24 is a reasonable amount. I think you'd maybe want higher than that. But, you know, 32 sounds plausible to me. Parsing. The design of a parser is mainly determined by the selection of the parsing technique and the error recovering strategy. Since the times of Pascal, Wirth's compilers use top-down recursive descent parsing. Recursive descent is the simplest and fastest parsing technique. This is what Per taught us in Bitwise as well with his ion stuff. So it seems like a pretty good way to go. Although there are more powerful techniques such as bottom-up LALR parsing, recursive descent is powerful enough if the syntax of the language is properly designed. Recursive descent parsing requires the grammar of the language to be LL1. That means it must be possible to analyze the language top-down from left to right with a single look-ahead symbol. Whenever there is an alternative in the grammar, the look-ahead symbol must lead the way and tell the compiler which alternative to select. This is probably also the way how humans read and analyze a program. Programmers read source code from left to right. Whenever they read a symbol, keyword, name, number, etc., they want to know which language construct it belongs to. In contrast, bottom-up parsers read symbols without already deciding to which language construct they belong. They simply push the symbols on a stack. As soon as the end of the stack contains an appropriate right-hand side of a production, they reduce this symbol sequence to the corresponding non-terminal symbol. Thus, bottom-up parsers delay the recognition of language constructs in a program as long as possible, which makes them much more powerful, but also less natural for humans. Programmers don't have large stacks in their heads. They do not want to read many symbols ahead until they know what a program construct means. Programs are notations for humans and not so much for machines. That kind of gets into Donald Knuth's ideas of literate programming as well. He really feels that programs are meant more for humans than they are for machines, and that the machine code that gets spit out from compiling a program is more of a secondary thing than the primary thing. And I think that there is a lot of value in the literate programming approach, and I'm interested in it personally, but I don't know if I'd say it's what everyone wants to do when they're writing programs. For one thing, I think it makes more sense to do literate programming after you're done with the design rather than during. I think when you're writing a program, it makes more sense to just write a program, but then afterwards you can go through and write a book about your program and transform your code into a literate program as you do that. But not everyone is an author. Not everyone wants to write books for people. So I don't know if that's really the way all programming should be done, but I think it's a great technique and it results in really great books for people to read about programming. So there's definitely value in the idea of programs being more for humans than for machines. There is some value to be had in going down that line of thinking. They should be easy to read and therefore suitable for top-down parsing because it is more natural than bottom-up parsing. Wirth always designed his languages so that recursive descent parsing could be applied. They did not compromise the flexibility or the power of the languages. I know of no language feature that must inherently be expressed in a way that is not amenable to recursive descent parsing. I even think that the availability of powerful bottom-up parser generators such as Yak are responsible for the cryptic syntax of C. If the designers of C were forced to make their language LL1, it would have probably become more readable. And I think looking at this from a historical perspective of where we are today, we know that a lot of languages go more this route where they focus on having it actually be I don't know if, for example, D is LL1 in particular, but a lot of languages kind of go this route of the simpler approach to their syntax, and it's definitely had big wins. I think it's definitely proven to be the right way to go, as opposed to C, how C does things. So, and that ties back into what we were talking about before, that I didn't know that C was designed using Yak. So that's kind of an interesting insight into why we ended up where we are. And unfortunately, even Wirth's languages contain a few constructs which are not LL1. To analyze such constructs, it is not sufficient to rely on syntactic information. One must also take semantic information into account. For example, a type guard, xt in Oberon, cannot be distinguished from a procedure call syntactically. One has to consult the symbol table to find out if X is a procedure or a variable. This ambiguity could have easily been avoided, for example, by using curly brackets instead of round brackets. The second design decision in a parser is the selection of an appropriate error handling technique. Although good error recovery is more difficult for hand-coded recursive descent parsers than for table-driven parsers, there are a number of suitable standard techniques. The general goal of error handling is to find as many errors as possible in a single compilation and to avoid spurious errors. In addition, error recovery should not slow down error-free parsing and should not blur the parsing code with too many error handling statements. The standard error recovery technique, which was also applied in the ETH Pascal and Modula 2 compilers, is to pass to every parsing procedure the set of follower symbols of the non-terminal that the procedure is to recognize. If an error is detected, the input is skipped until a symbol is found that is a legal follower of a currently active parsing procedure. The procedure stack is then unwound to the caller of this procedure and parsing can continue there. Something about this that's interesting to me, I've never really understood the idea of having a lot of errors in one compilation pass, because personally, and maybe this is just me, but when I compile a program, I always look at the errors, pick usually the first error on the list, and then go back in my code, fix that error, recompile the program, and repeat. I never really need to see more than one error at a time, because whenever there's an error, it's my job to go fix it, right? So, and I'm not gonna, like, maybe, and again, maybe this is just me, but I'm not gonna read through the list and remember every single error that it reported and then go fix them all in one pass. I'm gonna just look at the line number, jump back to my source code, jump to that line, fix the problem, and then, after I fix that problem, I need to re-see the errors that came after it to refresh myself, to get back the context of what other errors there are, as well as look up the next line number to go to. I'm not going to memorize every line number and then go fix them one after another. I'm going to do it one at a time. And I know many people use systems where you can just jump to the line number that you got from the errors. That can be automated. So that kind of eliminates the problem of memorizing line numbers. But again, I still don't know if I guess it makes sense if your compilation is low, because then you don't want to have to sit and wait for a recompilation every single time you're going to fix an error. Then I guess you do want to see a big list of errors. But if your compiler is sufficiently fast, I don't know if this really is necessary. I guess it's a good technique in general, because if your compilation does take a while, but that's something you're trying to avoid. So I don't know. I guess it depends. Like, if you look at the Jai programming language that Jonathan Blow is designing, what is like the largest piece of software that's going to be written in that language, and how long does it take to compile? Like, I know he's doing game development in that language, which is a great test of the language and also what the language is designed for. So, how long does it take him to compile whatever the current game he's working on? Like, how long does it take to compile that? Does it take a few seconds because it's a really big project? I don't know. I don't work at Tekla, so I have no idea, but it would be interesting to know, for a sufficiently large program, even if your compiler is super fast, does it get to be a reasonable amount of, like, a notable amount of time that you have to wait? Does it get to the point where you want to see a number of errors and fix them in batch? Or is it fast enough that even for a gigantic program, you'd be perfectly fine just doing a recompilation after every error? And I don't know the answer to that because I don't have the experience with large code bases written in a language that tries to compile as fast as possible. So I guess if you're being on the safe side, this is a good practice to follow. That's what I'd say about that. If you want to be on the safe side, you should probably do it this way. Although this technique can be systematically applied, or did I miss something? No, I think I read all that. Although this technique can be systematically applied, it requires a large amount of set operations and additional parameters of the parsing procedures. This slows down error-free parsing and tends to hide the parsing actions behind the error recovery statements. Therefore, Wirth selected a different error recovery strategy for his Oberon compiler. Okay, so what did he do? Given the fact that computers become faster and faster, it is not necessary anymore to find all errors in a single compilation. If a compilation takes less than a second, it is acceptable to find just some errors. Correct them and then compile the program again to find the remaining errors. Thus, the Oberon compiler does not synchronize with the followers of every non-terminal symbol, but selects a few synchronization points in the grammar where recovery is particularly easy and safe. These synchronization points are the beginning of a statement, a declaration, or a type where symbols such as if, while, type, or record are expected. Okay, so he doesn't go to the point of just bailing out at a single error, but he doesn't try to find all the errors either. He just tries to find some of them, which again I think is the correct approach. You don't want to see all the errors because oftentimes you'll end up in a situation where that's pages and pages and pages of errors, and you just want to see like the first 10 or something. So that's definitely reasonable in my opinion, and I think many languages do it this way today as well. Like I think D does it this way, where it doesn't find all the errors, it finds some errors, and when you recompile after fixing a few errors, some more might turn up after it. I think that's a pretty common technique these days. These symbols are considered particularly safe because they are unlikely to be encountered in the wrong context. If the parser detects an error, it reports it and continues up to the next synchronization point. That is to the beginning of the next statement, declaration, or type. There, it skips input symbols until one of the expected safe symbols occurs. Parsing can be resumed with that symbol. To avoid spurious error messages, an error is only reported if a certain number of tokens, for example 3, has been recognized successfully since the last error. Okay. So that sounds like a pretty reasonable approach in my opinion. This simple error recovery technique can be implemented in about 10 lines of code. It does not slow down error-free parsing and does not bury the parsing statements between error recovery actions. It is another example of Wirth's search for simplicity and adequacy. That kind of gets into the Mike Acton list we were talking about too. Like, I mean, I guess the first thing on his list was, can we do this not at all? And then can we do this only once, which would be like bailing out on the first error. But I guess if we say we don't want to, just bail out on the first error, the next thing is, can we do it, fewer times? Can we do it less often? And that's kind of what ended up being the sweet spot for error handling. So that kind of makes sense. Symbol table handling. Chapter 5. A symbol table maps the names in a program to their attributes, such as, let me just check the time here. Okay, we've got plenty of time. A symbol table maps the names in a program to their attributes, such as their types and their addresses. It consists of several subtables or scopes, one for every module, procedure, and record type. As a consequence of single-pass compilation, which Wirth preferred in his later compilers, the scopes can be organized in a stack-like way. A new scope is opened at the top of the stack whenever the parser encounters a procedure, and it is closed when the parser has finished with this procedure. Again, this sounds pretty standard. This has the advantage that most nodes of a scope can be discarded, are left for the garbage collector after the corresponding procedure has been parsed. Only the nodes for the formal parameters have to be kept. For the implementation of the symbol table, Wirth usually chose rather simple data structures such as binary search trees or even linear lists. Although a hash table would be more efficient for large scopes, it is more complicated to handle. For example, to traverse, to enlarge, or to shrink, and consumes more memory. Since too many names in a scope are often an indication of a questionable programming style, Wirth felt that large scopes should not be encouraged. Measurements showed that for procedure scopes, which usually don't contain more than 10 names, a simple linear list is sufficient. Symbol tables also store the types of objects, and again, as an aside here, I don't know off the top of my head how Pear handles this in his code. I'd have to check the code again, but that would be interesting to see how he chose to do the symbol table. I kind of think he uses the hash table stuff that he implemented quite early on, but I might be wrong about that. Symbol tables also store the types of objects. For type compatibility checks, Wirth again preferred the simpler technique, name equivalence, over the more powerful but also more complicated technique, structural equivalence. And I believe this gets into, again, I'm quite sure that Pear talked about this too in the design of his language. Like, I think languages have kind of converged on a pretty standard way to go about these things. Where for some things you prefer name equivalence, but there are other cases where you want structural equivalence. Most of the time you just want name equivalence. With name equivalence, two types are the same if they are denoted by the same type name, that is, by the same type nodes in the symbol table. This can be checked with a simple pointer comparison. In contrast with structural equivalence, as it is used in Modula 3, two types are the same if they have the same structure. That is, if they have the same components in the same order, and if these components are structurally equivalent pairwise. This requires a recursive comparison of the type structures and is not only more complicated, but also more time-consuming. A symbol table contains different kinds of objects, for example, constants, variables, procedures, etc., as well as different kinds of structures, for example, basic types, arrays, records, etc. Right. With type extension, which was introduced in Oberon, it would seem natural to organize the objects and structures in type hierarchies, that is, in an object-oriented way. There would be a base type with the common data of all object kinds, as well as several extensions with the special data for constants, variables, or procedures. Although this organization is elegant and is in fact recommended in some compiler books, it is complicated to handle in practice. I believe this is talking about the kind of thing D does, where everything inherits from object, or every class inherits from object at least, which is like a base class that everything inherits from. I know D does that. Since a compiler often works with general objects, their actual extension types would have to be checked using runtime type tests, and their fields would have to be accessed with guarded type conversions. Alternatively, all operations on objects could be defined in terms of dynamically bound methods, but this would require a large number of methods and would compromise the efficiency of the compiler. Besides, there are some operations which depend on more than one operand. This would require methods that are dynamically bound depending on two or more objects, so-called multi-methods. Thus, Wirth chose to represent the fields of all objects in a single flat record type, and to use only those fields that belong to the respective object variant. Although less elegant, this technique makes the access to object fields simple and efficient. It is another example of an engineering trade-off, which can be found so often in Wirth's compilers. That's something that I would definitely prefer Wirth's approach. I don't like the object-oriented approach at all, personally. Separate compilation. A major achievement of Modula 2 was the concept of separate compilation, which emerged in the 70s in languages such as Mesa, and later also Ada. In contrast to independent compilation, for example, as in Fortran and C, where subprograms can be compiled independently, separate compilation performs type checking across module boundaries, thus guaranteeing that separately compiled modules can be safely fit together by the linker. When a module is compiled, the symbol tables of the imported modules have to be made available as well so that the compiler can access the types of the imported modules. In order to do that, the module interfaces have to be described in so-called definition modules, that is, in files that contain the declarations of the exported objects. Instead of recompiling the interface of a module every time this module is imported, Wirth chose to store the precompiled symbol tables in so-called symbol files. Importing a module then simply requires the compiler to read the respective symbol file and to add the imported symbol table to the symbol table of the currently compiled module. Since symbol files are more compact than source files, they usually fit in a single disk block and can be read with a single disk access. A special problem is that the interface of a module can depend on the interfaces of other modules. This would require it to read several symbol files when a module is imported. In order to avoid this, symbol files are made self-contained. That is, they contain also parts of the symbol tables of those modules on which they depend. Thus, every import requires just one symbol file to be read. However, it can happen now that a partial symbol table of the symbol module gets imported twice from different symbol files. One has to make sure that these repeatedly imported symbol tables are consistent. This can be done by attaching to every interface a unique version number, either a timestamp derived from the compilation time of the interface or a fingerprint derived from the source code of the definition module. By comparing these version numbers, it can easily be checked if repeatedly imported symbol tables are the same. The version numbers of the imported modules are also stored in the object file of the importing module so that the linker can check if the object files to be linked match the interfaces that were seen during compilation. Thus, separate compilation not only performs type checking across module boundaries, but also makes sure that consistent versions of modules get bound together by the linker. Now, I'm pretty sure that pair doesn't do anything like this. I don't believe Ion has any such infrastructure in it. So it would be interesting because, you know, Ion has modules. It has a module system. It would be interesting to see, studying Pear's code, how he chose to go about implementing this. Because, like I say, I'm quite sure he doesn't have like special symbol files and like timestamping stuff and all this nonsense. In a recent dissertation, Regis Creelier refined the version checking between separately compiled modules and implemented it on a finer granularity. The problem with the basic version checking technique is that whenever the interface of a module is extended, it gets a new version number. This invalidates all modules that import this interface, even if they use only features that did not change. The new idea is to provide distinct version numbers for all exported objects instead of a single version number for the whole interface. If an object is added to the interface or some exported object is changed, the version numbers of the other objects in the interface remain unchanged. This technique gives a programmer much more flexibility in changing interfaces without having to recompile dependent modules. The implementation of this technique is non-trivial and is described in the citation here. That already, that's better than what you get in C or C++ when you do, what do they call it? Compiling, where you compile everything to object files and then you only recompile object files as necessary. Like, that's basically what he's talking about with, you know, module level versioning, right? That's kind of the same thing in my mind, at least. Maybe I'm not totally understanding, but it sounds like that's kind of what he's talking about implementing here. And having it more granular prevents the problem where, you know, you make a change and then you need to recompile a bunch of object files that really shouldn't need to be recompiled, but because it's at the, you know, the object file level, you run into that problem that it's not granular enough. It sounds like that's kind of what this is addressing. But again, like I say, in Ion you don't have any of this nonsense, and in D you don't have any of this nonsense either. So I don't know, man. Seems like maybe this sort of thing can be avoided altogether, depending on how you go about things. And I think maybe the way that he achieves this in Ion, now that I think about it, is that everything is done as a Unity build. I believe that's the approach that Pear is taking, that everything is compiled like Unity style, Unity build style, which is like what you do, what I do in the pcalc program, for example, too, just by convention. I think that's the reason Pear doesn't need infrastructure like this. But I might be misunderstanding, and I might be totally wrong about that. So take that with a grain of salt. As a surprise to the software engineering community, Wirth abandoned the definition modules in Oberon. However, he did not abandon the concept of separate compilation, but only the necessity to write down a definition module explicitly. In Oberon, there are just implementation modules. The programmer simply marks those declarations that are to be exported in the source code, and the compiler generates a symbol file from them during the normal compilation. A definition module can still be generated from the symbol file of a module, but it is only documentation. A similar technique is also used in other modern languages such as Eiffel and Java. And this is the sort of thing that D does as well. You can, well, I don't know if you can even do that anymore. I know you used to be able to generate a file that's kind of equivalent to like a header, so to speak. Like it would just give you like forward declarations of everything, but not actually implementations. I don't even remember what that feature was called, and I never used it. I don't know if it was actually useful and if that's actually something that D still has, but I know D had something like this at one point. The elimination of explicit definition modules caused much debate among Modula 2 enthusiasts. In fact, there are good arguments in favor of definition modules, but there are also good arguments against them. A definition module is a clear description of a module interface. It forces a programmer to think on the design of a module first before starting its implementation. This is good software engineering practice. On the other hand, definition modules introduce redundancy into a language. For example, the interfaces of exported procedures have to be displayed both in the definition module and in the implementation module. Every time a procedure interface is modified, it has to be modified in two places, and the compiler has to check the consistency of these declarations. Definition modules also make it harder to selectively export record fields because the record with the exported fields would have to be declared in the definition module and the rest of the record in the implementation module. Finally, explicit definition modules duplicate the number of source files and make it harder to maintain a large software system. And again, I think this is something that modern languages have kind of all agreed upon, that you don't really want what Worth is calling these definition modules, or headers if you're thinking of like C or C++, right? You don't really want headers. Modern languages all, as far as I know, like all the major kind of improvements upon C or C++, that whole kind of generation of languages doesn't use them. It follows this approach that Worth apparently decided he preferred. Personally, I think that the elimination of definition modules was a good decision since it simplifies the language and its compiler. One can still start with designing the interface of a module by writing a skeleton of the implementation module that only contains the exported declarations. Later, the skeleton can be filled with flesh by by adding private declarations in code. Nevertheless, I must admit that it is tempting to mark the exported declarations only after the whole implementation module has been written. Yeah, I agree with this author that I think definition modules, as they're calling it here, are kind of going the way of the dinosaur. I don't think they're really necessary or useful. I think it's better to go without them. And that is definitely what Hula is going to be doing. I'm going to be not having any sort of headers. It's just going to be implementation files. Code generation, chapter 7. The code generation phase is not as systematical. Systematical? Is that a word? Systematical? That doesn't sound like a word to me. Maybe it is. Systematical. Maybe it is a proper word. Sorry for getting distracted here by by grammar. Okay, so according to Grammarist, it is not a word. That's what I thought. I don't think systematical is a word there, Mr. Mr. Hans Peter. But anyway, the code generation phase is not as systematic to describe and to implement as the earlier compiler phases. It heavily depends on the peculiarities of the target machine. which is often irregular and full of machine-specific details. Nevertheless, the code generators of Worth's compilers show some common characteristics. One principle that was already mentioned earlier is to generate reasonably good code from the beginning. This can be achieved by delayed code generation using the item technique described below, by exploiting the special instructions and addressing modes of the target machine, and by applying simple optimizations such as constant folding and strength reduction. The spine of Worth's code generators is what I call the item technique. It is described in Worth's compiler book, although it is not given a specific name. The general idea is that every value that turns up during code generation is described by a structure that is called an item. Items can describe constants, variables, intermediate results, or condition codes resulting from compare instructions. Every parsing procedure processes a language construct and returns an item that describes the value of this construct. Items are thus the attributes of the imaginary syntax tree. While the parsing procedures move top-down, the resulting items are propagated bottom-up, thus creating more complex items and generating code alongside. For example, the code generation for the addition x plus y first leads to two items describing the variables x and y. In the next step, load instructions are generated for x and y, and the items describing the variables are transformed into items describing register contents, because the values of x and y are now in registers. Finally, an add instruction is emitted, and the two register items are combined into a single register item, which describes the result of the addition. If the target machine supports the addition of memory operands, only x has to be loaded into a register and y is still described by a variable item. And of course, risc-v does not support memory operands, so that's irrelevant to us. We of course do load everything into registers. In many cases, items can be constructed without emitting code. For example, a record selection r.f results in an item described by the record variable r and an object describing the field f. In the next step, a new item is constructed that describes a memory cell with the base address of r and the offset of f. No code has to be emitted in this step. The transformation just leads to a compile time addition of an offset. Using compile time operations, code generation is delayed as long as possible. An instruction is only generated if the result of the transformation cannot be produced at compile time. The kinds of items depend both on the source language and on the target machine. For every object kind in the symbol table, for example, for constants, variables, fields, procedures, etc., an item kind has to be provided that describes that object. These are the source level items. Similarly, for every addressing mode of the target machine, that is for immediate, register, register relative, indexed, etc., an item kind has to be provided that describes a value accessed by this addressing mode. And again, this is going to be simpler on risc-v due to it being a simple architecture. These are the machine level items. Code generation proceeds by transforming source level items, for example variables, into machine level items accessed by a specific addressing mode, for example register relative. All items are implemented by a flat record that encodes the item kind and its attributes. Usually some source level items are identical to some machine level items. For example, a constant item corresponds to an immediate item. A variable item corresponds to a register relative item, etc. In this case, the two item kinds can be combined into a single item kind. Having identified the necessary item kinds, one has to implement three sets of procedures. The first of which, procedures that transform objects into source level items. For example, variable objects into variable items. Second of which, procedures that transform one item kind into another, for example, from register relative to register by loading the value into a register. And third of which, procedures that generate the actual machine instructions. For every machine instruction, op A, B, one has to implement a procedure, op A, B, where the parameters A and B are items. This procedure is implemented by a case statement, considering all possible combinations of item kinds that A and B can assume. By applying these guidelines, item kinds and the corresponding code generation procedures can be developed systematically for any given machine. Another important issue in code generation is register allocation. It isn't especially important for RISC machines where a large number of registers are available and should be exploited to have faster access to variables and intermediate values. And this is something that I've said too that I want to do for Hula, that I want to have one of the optimizations that I actually want to do is like doing the best register allocation that we can possibly do. I think that is very important, and this author apparently agrees, and I guess Worth agrees too, since that's what this is all about. Good register allocation, however, cannot be done in a single pass. It requires life range analysis of programs and a coverage of the life ranges by registers using a technique that is based on graph coloring. Okay, that's interesting. I understand the idea behind register allocation. Like if I'm writing assembly code, I know how to do it by hand, right? I know how to put things in the optimal places in registers, and I feel like I can take what I'm doing in my head and write it out as a procedure, but I definitely don't have the formal background in stuff like graph theory. Like the idea of using the technique of that's based on graph coloring is something that's definitely foreign to me. That's not something I've ever heard of. And so I think rather than just taking what I kind of conceptually know and trying to write it out as a procedure, it'll probably be good to study some of the classic works on this sort of thing. You know, read some research papers on the state of the art in register allocation, and you know, go through the LCC book on the book club series, and see how Pear does things as well, although I don't know if he's going to be doing any fancy register allocation in his language. But I don't want to, that's kind of why I don't want to jump into implementing Hula right away still. Even though I've seen Pear implement Ion, I haven't really started on Hula. Other than what I showed on the very first Bitwise homework day of kind of, you know, this is what's in my head, but I haven't done any implementation details. And I'm kind of waiting on that because I still want to do more research and learn more about compiler construction before I start actually implementing that. And that's kind of also what pcalc is helping for. Pcalc doesn't need to do stuff like code generation, but it's kind of getting my feet wet in compiler construction because, well, in the case of pcalc, it's not really a compiler, it's an interpreter, but the concepts are largely the same and the structure is largely the same. It's just that it, you know, it kind of stops at the parsing stage, because when you would normally be parsing, you're actually evaluating. But that's like the only thing I've done, is I've been working on the pcalc language stuff. I'm waiting on the Hula stuff to learn more about this sort of thing. Since Worth's compilers do code generation in a single pass, a trade-off is used. The basic register allocation technique Hello, Cyanox. Uh, I'm reading through this paper. It's it's what Pear linked on day 9 of Bitwise. If you don't follow Bitwise, by the way, check out bitwise.handmade-network, and you'll see his project. And what I'm doing is I'm reading through a paper that he linked on day 9 of his series. It's compiler construction, the art of Nicholas Worth. So I'm giving that a read today on stream, and kind of giving my own thoughts as I go through it. So since his compilers do code generation in a single pass, a trade-off is used. The basic register allocation technique is quite simple. Whenever a new register is needed, the register allocator returns an arbitrary free register and marks it as used. At the end of every statement, all registers are returned. This technique is simple and efficient, but does only exploit a small subset of the available registers. As a simple optimization, a compiler can try to keep the first few variables of every procedure in registers. However, this can only be done if these variables are not accessed by nested procedures, and if they are not passed to other procedures as reference parameters. Instead of allocating a memory cell for such register variables, the simple table simply holds the register numbers where these variables are stored. Of course, register variables must not be marked as free at the end of every statement. One also has to save and restore register variables across procedure calls, since the called procedures will use the registers for their own variables. A detailed description of this technique can be found in one of the citations. I don't think for Hula personally I'll be doing something like that. I'm definitely going to try to do the optimal register allocation, which is more complicated. I feel like that's really the proper way to go. I don't think we want to compromise on register allocation personally. Okay, chapter 8, single pass versus multi-pass compilers. Worth designed his languages so that they can be compiled in a single pass. Every name has to be declared before it is used. Pointers and procedures can be forward declared in order to allow cyclic dependencies. If it was necessary a few years ago to decompose a compiler into several passes due to memory restrictions, this is not an argument anymore. Current computers have enough memory to fit a whole compiler into it. The predominant reason for multi-pass compilers is optimization. Advanced optimization techniques require data flow analysis, which has to be performed on an intermediate program representation, such as the control flow graph. Building this graph and analyzing it requires several passes. Worth's compilers avoid sophisticated optimizations, thus no intermediate program representation is necessary, and the code can be generated on the fly during parsing. Although the resulting code is not as efficient as it could be, it compares well with the code generated by optimizing C compilers on most platforms. Measurements are given in a citation again. So this is one thing that's interesting about this this note here is they talk about how everything has to be declared in order. That's one thing that Pear doesn't do. He allows out of order declarations and stuff. And it seems like it's not too hard to do that. So I don't know if you really want single pass or not. And again, if you're doing advanced, like the state of the art in register allocation, you might, not want to do code generation during the parsing stage either. That might need to be separated out in order to implement whatever the best way to do that is, which I don't know. Yes, Cyanox, I will be implementing a compiler on my series, and that's what Pear already did on his series as well. Well, he did a transpiler. It's not a full blown compiler right now. But yeah, that's what he did on oh on Bitwise, which is Paris project. He implemented his own language called Ion, and right now it compiles down to C. And then you compile the C code to actually get an executable. And I'm going to be doing my own language as well, which is called Hula. And I'm also going to be going through, before I do that, I'm going to be going through the LCC book and implementing a C89 compiler. Or not really implementing it myself, but following along with their implementation of it and typing out all the code. So that's what I'm planning on doing. I'll be typing out the code for the LCC C89 compiler to learn everything I can learn from that, and I'll be doing some other research, and then eventually I'll be implementing my own language as well. Thank you. I definitely will. Have fun. So we're on chapter 8 here, single pass versus multipass. There is, however, another good reason to decompose a compiler into two passes, namely portability. If a compiler is decomposed in a language-dependent frontend and a machine-dependent backend, porting the compiler to a new machine only requires to rewrite the backend, and yeah, that's definitely something we want to do. And I believe that Pair is going to do it this way as well. I'm not totally positive on that because right now he's just generating C code. But I think when he gets to the point that he's generating machine code directly, I believe he would structure it this way. And I know this is how LCC structures their compiler as well for C. So that seems like the way to go. This solution was chosen in the Oberon OP2 compiler, designed by risc-v and ported to about 10 different platforms by various PhD students. All of these compilers use the same front end, which contains the scanner, the parser, and the symbol table handler. It generates an intermediate program representation in the form of an abstract syntax tree and a symbol table. These data structures are passed to the backend, which contains the code generator. The syntax tree also allows for more optimizations in the backend, such as the elimination of array index checks in certain situations. The backend for the IBM RS6000 even applies heavy optimizations before code is generated. It turned out that this multiscalar processor requires instruction scheduling to achieve a code quality comparable to the code generated by optimizing C compilers. Therefore, the syntax tree is first transformed into a control flow graph using a simplified version of the static single assignment form, or SSA, as it's commonly known. Various optimizations such as common sub-expression elimination, constant propagation, loop invariant code motion, and instruction scheduling are applied to this graph before code is generated. And again, even if we're structuring it, if we end up structuring it this way, that doesn't mean that we're necessarily going to be implementing all kinds of optimizations on it. We're only going to be implementing a few select optimizations that seem necessary. Like I say, the register allocation should be as good as possible. And I think we want some constant folding as well, maybe. Because, for example, if you have an array index, which needs to be known at compile time, but you want it to be an expression, you would need to constant fold that. So there might be good reasons that you need to implement constant folding. The intermediate program representation between front-end and back-end turned out to be of value for still another purpose, mobile code. Michael France found a compact encoding of the syntax tree and the symbol table that can be transferred over a network to some target machine, where it is compiled to machine code by a code generating loader. This is an alternative to the Java bytecodes and allows write once, run everywhere software. It is interesting to note that this idea was published before the advent of Java. Uh, Chapter 9, Conclusion. This paper tried to highlight some principles that I believe are central in Worth's compilers. Maybe my view is biased and incomplete, but I think that it reflects some valuable ideas. I always enjoyed studying Worth's compilers, although they contain hardly a line of comment. Their structure is so clear, simple, and elegant that they are a pleasure to read. The full source code of some of his compilers can be found in his books on compiler construction and on the Oberon project. The source code of the OP2 compiler is also available online from ETH Zurich as part of the Oberon distribution. For Worth, compiler construction is an engineering discipline and not pure science. He prefers well-proven techniques over fashionable results. For him, a compiler is a tool that has to be useful and practical as possible, and not as much a piece of scientific experimentation. I regard Worth's way of compiler construction as an art, not in the sense of black magic, but in the sense of a craft built on 4 decades of experience. So yeah, based on, from reading this paper, I'd say the takeaway is really that that Nicholas Worth kind of was one of the early pioneers of a lot of the ideas that I think are the right way to go in compiler construction. Like the vast majority of this, I felt like a lot of it was either principles that apply very broadly to pretty much any software, to a lot of ideas that are becoming pretty common in modern languages today in how they go about implementing things, or things that just sound like really good ideas to me that I want to do in my own compiler, like the general idea of not having the compiler be super sophisticated in terms of optimization. And I, from reading this, what I would say is Worth was probably one of the early people in a much larger school of thought, like people like Donald Knuth, Daniel Bernstein, I think his name is, Pear, of course, Jonathan Blow. I feel like there's a whole school of thought here, and I guess this kind of gives us the historical background of one of the people that really kind of pioneered a lot of these ideas. So that was a fun read. I enjoyed that. How much time do we have here? Looks like I've been streaming for around 2 hours, or I mean, like the episode is around 2 hours and some minutes right now. How long is this? Not super long. I think we're gonna try to go through this today. We might not read the whole thing, but this is from Sean Barrett, a performance comparison of Judy to hash tables. And I don't remember when I read this, but I know I already read this some time back, quite a while back. But I don't remember any of the details, and it's not like I studied it in depth or anything. But we're gonna give it a read here. So Judy, pros and cons. And by the way, what is the day that this was from? Day 12. So this is the day 12 paper that he linked. So Judy is a high-performance, low-memory usage data structure that implements an associative array. So it's a fancy hash table, is what he's saying. Judy has 2 main strategies. Use a 256 array tree, compressed, and engineer the compression to generally require 1, at most 2 secondary cache misses per tree node probe, so that very large data structures are efficient in both size and speed. Cyanox says not all associative arrays are hash tables. That's true. I guess Hash table is, I shouldn't say that because hash table is one way to implement an associative arrays, but what we're looking at is an alternative, I guess, is what would be the proper way to phrase it. You say Judy arrays are mostly trees, so we're gonna see the details here. Numerous claims about Judy's performance are made in the Judy white paper. I don't think any of these claims are wrong. However, it does not appear that sufficient effort was put in benchmarking Judy against other data structures. Now, it is unlikely there is another data structure that is both as fast and as small as Judy is. But it is easy to come away from reading about Judy getting the impression that because it is small and hence more cache friendly, it will be faster than something larger. For example, look at the discussion about tunneling under the time-space trade-off curve. This is not necessarily the case. If in the end what matters is performance, the only thing to do is measure performance, not space. There are a few potential disadvantages to keep in mind about the Judy approach. Its author argues that approaching the problem as engineering means accepting that complexity is how you get good performance. Simplicity is for theoreticians, but this complexity leads to things like a data structure with 20,000 lines of code designed on the assumption that a cache line is 64 bytes being used primarily on machines with 32-byte cache lines. A redesign optimized for 32-byte cache lines would come close to starting from scratch. Additionally, some of Judy's space and speed improvements come from strategies that could be used by any data structure, but aren't because they're not good software engineering. Most abstract data types give you a fixed pointer good for the life of that data type. Judy omits one level of indirection and gives you a pointer that may change during the life of the associative array as it grows and shrinks. If you want multiple objects to have pointers to the same Judy array, you'll need to wrap the changing pointer in another data structure, just like how data structures are normally. Judy saves space by encoding information in the bottom bits of the pointer. This would interfere with any other use of the bottom bits. For example, in a language that uses tagged boxed data like OCaml. Cyanox says this article is dated 2003. Practically all x86 machines today use 64-byte cache lines. That's a good point. Also, thank you for the host. I appreciate it. That's a very good point to point out that today 64 cache lines are pretty much universal. And this article is a little dated. A simple hash table. The Judy white paper mentions comparisons to hash tables, but from the description, oh, thank you for the follow as well. From the description, they appear to have tested fixed size hash tables with external chaining. Such structures have performance O of n with a very small constant, 1 over m, where m is the size of the hash table. Proper hash tables have performance O1. For this comparison, I wrote a hash table data type with the same interface as Judy. An associative array type whose key and value are both 32 bits. Alright, I used a hash table with secondary hashing, internal chaining, using a table size of a power of 2 that periodically doubles, rehashing all the elements. The arbitrary doubling threshold I picked for the initial implementation was 65% full, and although I included a command line option for tuning it, I never did. For the first time in my life, I also wrote code that caused the table to shrink by a factor of 2. The default here is if it gets under 30% full. That's interesting. The difference between 65% and 2 times 30% is intentional to avoid hash table resize thrashing. Right, that makes sense. Also, the hash table rehashes all the elements if the table reaches 80% full of real entries and deleted markers. On deletion in a hash table with internal chaining, you have to leave a marker that allows you to keep probing past the deletion. With repeated insertion and deletions, the table must become full of deletion markers and have very poor performance. Cyanoic says that initial comparison is ridiculous. Lol. I don't know. Are you reading ahead, or are you talking about the comparison he's talking about here of how he's just created an associative array whose key and value are 32 bits? I mean, I haven't read the details of Judy, so yeah, it's definitely good that Sean took the time to test the claims of the Judy array author. I think in general that's something that people should do, rather than just taking a research paper for granted, so to speak. Yeah, I definitely completely agree with the argument in favor of good engineering practice too. But yeah, I don't know the details of Judy, and I don't know, if this is truly a fair comparison. But one thing I want to point out too is I believe that Pear did, in his hash table implementation, he did something similar to this too, where I don't remember the percentage he picked, but I think it was around like 50% where he would do this as well. The doubling threshold, I mean. I don't think he did a shrinking thing. And he says, Cyanoic says, do you know trees? I don't know if that's pronounced trees. I think it is. And I've heard of them. And I'm sure I've read the Wikipedia page on them at some point. But off the top of my head, no, I know nothing about them. Tries, okay. Yeah, I don't. I'm aware of them, but that's the extent of my knowledge. They're very interesting data structures. Yeah, I need to at some point study data structures more. I don't have an adequate background in data structures. That's something I lack in. Yeah, Judy's array is basically a fine-tuned compressed trie. Yeah, that's basically what Sean said here. He called it a tree rather than a trie, but I'll take your word for it that it's a trie. He says it's a 256 array tree compressed. On deletion in a hash table with internal, oh yeah, we read this. Tries are also called radix trees. Okay. Interesting. For full compatibility with Judy, 2 values were chosen as out of band to represent empty and deleted slots in the hash table. That's interesting that he has 2 different values to represent empty and deleted. The main data structure that keeps data about the hash table contains 2 Boolean flags for whether the corresponding keys are currently in the associative array, and 2 values representing their associated values, if so that these keys will never appear in the hash table legitimately, and thus are safe to use out of band. Traditionally, hash tables are often hashing pointers and can use null pointers or misaligned pointers as out of band values. And again, I believe that's what Pear does in his implementation. He uses null pointers for that purpose. I put some effort into trying to early out of the hash table routines quickly. For example, if the first probe is a hit, the secondary hash is never computed. The hash table implementation is about 200 lines of C code and can be read here. Let's take a look. Okay, hash table implementation. It has a hash word. He's using Bob Jenkins' mix function, possibly overkill for only 32 bits, but a simpler one was no faster, so what the heck. Okay, he says this magic constant here is the golden ratio, an arbitrary value. This is another thing about hashing in general. It seems like kind of black magic to me. I don't know if there are good resources out there to learn about like the details of how hash tables are constructed and like why certain magic constants are chosen and things like that, because it really seems like black magic to me. I'd love to know about any resources to expand my knowledge in you know, understanding how hash tables actually work. Ah, yeah, of course, the art of computer programming. I really need to get a copy of the art of computer programming. I don't have it, but I'd like a physical copy. I know it's many volumes and pretty spendy, but I feel like that would be a worthwhile thing to get. So I might want to look into that at some point. Okay, so he has key null and key deleted. And then an item structure which has key and value, which are just uint32s. Then the hash structure has a mask, a list of items called data, has key, which is an array of 2 integers, a value, which is an array of 2 uint32s to handle out-of-bound values, the data length, population, deletes, grow size, shrink size, delete size. So he says he's caching these things for speed, and then he also has a void pointer, free pointer. Okay. And then overage is defined to be 1. He says allocate extra because of either weird memory errors in Win98 or a bug in the hash table code itself. Okay. Hash create. So he mallocs size of the pointer to h. If size is less than 8, size equals 8. Okay, what was... Oh, size is what we passed in, okay. He asserts non-greater power of 2, size equals size. H data length equals size, okay. Mask is size minus 1. I don't understand what the mask is going to be for yet. And I don't know the details of what the values he's caching are going to be for. But we have population equals h deletes equals 0. Haskey 0 equals haskey 1 equals 0. Grow size, okay. Grow size is size times hash table max full minus 1. Cyanoak says mask is probably to make indexes fit in the hash table. Okay, that makes sense. Yeah, that with it being size minus 1, that definitely makes sense then. Okay, grow size. So hash table max full times size -1. I'm not sure if I totally follow that. But he says if grow size is less than 2, grow size equals 2, okay. Shrink size is going to be size times hash table empty. Okay. If the data length is 8, shrink size is 0. Okay. Delete size is size times hash delete rehash -1. Then we allocate data, clearing it to 0. So, okay. Free pointer is set to data. And then we do data plus equals overage. So the overage is the extra space we're allocating because of weird memory errors in Win98 or a bug in the hash table itself. Okay. And so I take it we're just skipping over the memory in the beginning with the data plus equals overage. We're skipping over the extra memory in the beginning of it. But then we return h. Okay. So I don't follow everything about how he's initializing the hash table. Some of the specifics I'm not totally following, like how he's choosing the grow size, the shrink size, the delete size. And we have a hash free, which looks pretty straightforward. We have a hash find. So okay, so this is taking our hash table and our key. I don't know if I'd say it's not the most readable code. It seems perfectly readable to me. It's just that I feel like my lack of understanding some of these lines is less to do with the readability of the code and more to do with my unfamiliarity with the implementation of hash tables. I don't really feel, personally, I don't feel comfortable saying it's just because the code is unreadable. I'm not gonna write it off as that personally. So we have hash find, which is taking our key and returning a uint32 pointer, which is presumably our value in the hash table. So we have D is going to be the hash, Z is going to be an item, and it's set to D data. Oh, okay, you're picky about style? I'm not very picky about style personally. So we're starting Z at just the first element of data. And we have our mask, which is the mask from the hash table. H is going to be hash word of key. P is H and mask. So yeah, that's the modulo to make sure it's in range. Okay, you've worked quite a lot with hash tables. I'm opposite of that. I have not. So S we have an s variable. If key is less than equal to key deleted, and if d has key, so if the hash table has the key, and the key is less than or equal to deleted, then we return value indexed by key. Okay. That seems straightforward enough. If z, which again is the data, if z indexed by p, which is the hash of the key, fit to the size of the table, if the key of that element within data is equal to key, then we return the value from that. And if the key is null, we return null. Okay. And then we have s is equal to h shifted right 16, ORed with h shifted left 16, and ANDed with the mask, ORed with 1. Okay, now that line I don't understand. That line I do not understand right there. But h is 32 bits, right? So 16 is half of 32. So this is swapping the endianness of h, of the hash of the key. We're swapping the endianness. We're ANDing it with the mask. So that's the same as the computation of p. It's just that it's the byte swapped version of that. But then we're also ORing it with 1. So I still don't totally understand. Like, I don't understand the ORing it with 1 part, and I don't understand why we're byte swapping. Then we're asserting. Okay, fair enough, Synox, fair enough. So the population plus the deletes does not equal data length is what we're asserting. And then we've got a do while loop. So p, which again is the hash, but within range of the size of the number of elements we have, right? So p is equal to p plus s ANDed with the mask. Okay. So it seems like this is doing the search. Like if you index into it and you don't hit the value right away, then you need to search down the hash table, right? But he's not searching, like, it's not a linear search. It's jumping by this. Yeah, exactly. On collision, it finds another slot in the table. But it seems like he's not just going to the next slot. It's moving by whatever this computes to, because like that's what this is doing, right? Like he's incrementing p by s and then making sure it's in range. So this will wrap around if it goes over. And then if z indexed by p.key equals key, return the value, and you just keep doing that search. Yeah. Okay, so you're saying this is double hashing, and the swap ord with 1 is the second hashing. Okay, I'm not familiar with double hashing, so I'm not familiar with that concept, but that's helpful information, definitely. And we do this while the key is not null. So that seems like a pretty standard search, and you're saying it's just using the technique of double hashing to do the search, rather than just a linear progression. So I don't understand the details of double hashing or why you would do it, as opposed to just incrementing the pointer, for example. But I think we've got a decent understanding of hash find. The other thing I don't totally understand is this case here. If the key is less than or equal to deleted, I don't really understand that bit either. Okay, so Cyanoak says linear probing can easily build long collision chains. So, okay, so double hashing is less likely to, like you say. Okay, that makes sense. So that's just, by doing it this way, we're just making it less likely to have chains of collisions. Okay. I still don't totally follow the implementation of it, but I get the concept now. Okay, and then we have rehash. So rehash takes a length and it does a hash create length. It increments rehashes, so we're keeping track of how many times we've rehashed. Yeah, rehash is probably used on resizes. That makes sense. That's what Pear does in his hash table implementation as well, so that makes sense to me. And yeah, so we're just going to loop over the existing hash table and rehash every item in it. And so that's, we see we're doing hash insert on the new hash table. We make sure stuff is still good. Then we free the old and we are going to return the new one, right? So it has some other bookkeeping that it needs to do for the has key and the value stuff, which again, I don't totally understand. We memcopy some stuff and then we free. Oh, I see. We're memcopying the new one we've allocated. We're not returning it. We're overwriting H. So that's what we're doing there. That makes sense. So again, I feel like I mostly understand rehash. That one's pretty simple. It's just the extra bookkeeping we're doing right here that I'm not totally understanding. Then we have hash insert. So this is actually putting a key into the table. So we get the hash table into D. We get the data into Z, same convention as before. The mask. We have a value F, which is set to -1. I don't know what that's going to be for. H is the hash word of the key. P is H ANDed with the mask. And we have S again. And so again, we have the case where key is less than or equal to key deleted. So then we say has key indexed by key equals 1. And then we return the value indexed by key. Okay. Still don't really understand what's going on there, but so then if z indexed by p.key equals key, we return the value. If zp.key equals key deleted, f equals p. Okay, so f is starting as -1, but we're setting it to p if the key is deleted. Okay, so the -1 is probably just because that'll never be, that's a, you know, a value that it'll never be otherwise. So we're keeping track of whether the key was deleted, basically. And then if the key is greater than key null, we do the double hashing that we saw earlier, and then we do the search as expected. And then here we have the bit about the key deleted. I don't know, I feel like I'm following it, Cyanox, as much as I, you know, I mean, I'm limited by my lack of understanding, but I feel like I'm following it well enough. Thank you for complimenting my bravery. So this one is different from the one we saw earlier, in that this one has the case for if the key is deleted and if f is equal to -1. So while we're searching, if we haven't deleted, if we haven't found, okay, so f must stand for found, right? Found the deleted key. If we found that the key is deleted, we set f to p, right? But here we're saying while we're searching, if we find that the key is deleted and we haven't already set it to deleted, then we set it to deleted. So that makes sense, right? So I feel like I'm actually following what's going on with the f variable in this code. And we're doing this while the key is not key null. So then we have if the key does equal key null. So this is the case where we haven't inserted the key yet. So the key doesn't already exist in the hash table at this point. And the population is greater than or equal to the grow size, then we need to rehash the table. We're actually going to grow our hash table. So we do a rehash with a bigger data length, we double it, and then we return hash insert hash key. So we insert it after we've grown the hash table. Otherwise, if population plus deletes is greater than delete size, in that case we rehash it as well. Okay, I still don't understand the delete stuff. I mean, I follow the stuff of what we're doing with f, but I don't understand exactly what this is used for yet. But I understand what we're doing here is that if this case happens, we're doing, you know, we're just growing it again in the same way that we do here. Or no, we're not actually growing it, but we're rehashing it. See, this isn't growing it, it's just rehashing. So we're forcing a rehash in this case without actually growing the thing. So he said something about that in this paper we're looking at here. I remember he talked about the hash table rehashes all the elements in the table if the table reaches 80% full of real entries and deleted markers. Okay, deleted slots are usually called tombstones, and Cyanox has a link to some research about that. I'll definitely check that out, but I'm not going to do it on stream because we're already running out of time here for the day. I wanted to just read through this paper, but it seems like we're probably only going to get a walkthrough of the code he implemented here. But like I say, I'll check out that research off stream later as well. Okay. But yeah, so that's what's happening here. If it's 80% full, including the deletion, the deleted markers, then we do a rehash. That's what this code right here is doing. Then he says, else if f is greater than or equal to 0, then p equals f. Well, if f is greater than or equal to 0, shouldn't f equal p? Oh, because of the rehash, right? Or no, but because this is an else if. So it wouldn't have gotten rehashed, would it? If we hit that case? It doesn't look like it would have ever gotten rehashed. I don't understand why you're setting p equal to f here. I think p should already equal f. Unless I'm misunderstanding something. Oh, no, 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 no. Yeah, it's because we're advancing p right here. Yeah, yeah, yeah. Okay. F is just caching p. Yeah, I got it. I got it, Cyanox. I'm following now. And then if the key is deleted, we subtract 1 from deletes. That'll maybe make more sense. I feel like all this deleted stuff is going to make more sense to me after I read the research you linked me. But like I say, I'm going to do that off stream. I mean, hey, we figured it out. So key is equal to key. And then we increase the population by 1. That makes sense. Like, I think I understand the population at least. The population is the number of entries, right, that aren't deleted. And then we're returning the value after we've done all that. So the deletion stuff, I take it that if a key is deleted, we don't actually delete it. We're keeping it around in the deletes, right? And then if we end up setting the key in the hash table again, we're just relinking it. Is that what's going on here? Okay, okay, awesome. So that makes sense. And we're pretty close to the end here in terms of how much code we have left to go through. And I'm getting close to being out of time for the day too, so we're gonna finish up reading this code and then call it a day. So hash delete. It takes the key to delete. So we have H for the hash table, P for the item, value equals hash find. So we find the value from the hash table using the key. If the value is null, we return 0. If the key is less than or equal to key deleted, okay, the key deleted stuff is making more sense now too, because so here we're saying if it has key, then, or if it's less than or equal to key deleted, has key equals 0, return 1. So again, I still don't know if I fully follow it, but it's starting to make more sense to me that how the deleteds are keeping a cache of things that were previously in the table around. So P equals value minus 1. P key equals key deleted. We minus, so we subtract 1 from the population, add 1 to the delete. That makes sense. I don't know if I follow the backing up one from the value, but I'm following this. If the population is less than the shrink size, we do a rehash. Okay, and this is doing the actual shrinking here. We're having cutting the size in half. Okay, I'm glad I'm not alone in that. And then population plus deletes, if that's the case, if it's greater than or equal to delete size, we do a rehash. And then we return 1. So the int is actually a bool, and we're returning 0 if it's not in the table, and if we successfully delete it because it is, that's when we return 1. I understand the shrinking, and I don't know if I understand this case where we do a rehash. I guess this is the same case as we saw before, like this up here, right? Where if it's, like we said before, if the table reaches 80% full of real entries and deleted markers, we rehash. So it's just, it needs to do that when you do a delete as well. Okay, and the second rehash gets rid of tombstones if there are too many. Okay. Okay, that makes sense. That's interesting to know. The other thing, one subtlety to point out here is this is greater than or equal to, whereas previously in the case of an insert, I think it was. Yeah, in the case of an insert, it's a greater than. Yeah, okay, that makes sense because it does the insertion, whereas this isn't inserting. So yeah, I follow that. Okay. Hash count. So it takes the hash, it returns population plus has key null plus has key key deleted. So again, I don't understand the has key stuff. But then we have hash mem, which returns size of hash plus size of item times hash pointer hash data length. So item times data length, that gives you the memory usage of all the data, right? And then you're also adding the size of the hash table itself. Okay, that makes sense. So that's giving you the actual memory usage of the hash table. And with that, I think we're going to call it a day here. I wouldn't say I understand everything about this implementation, but I think we covered some pretty broad strokes here. We understand a lot of it, and we read through the whole thing. So that's a pretty good day's study. And I'll continue to study this more off stream when I can. And then next time we'll continue finishing up reading this paper, and I'll hopefully have a better background in this implementation at least. And I'll maybe read up on the Judy array stuff as well. But anyway, thank you everyone who tuned in today, and I'll see you guys in the next one whenever I stream next.